variables. Now I can have something like, you can see here, my y response variable is miles per gallon, and the independent variables are cylinders, displacement, horsepower, weight, and acceleration. So now tell me how cylinder is coming to a picture if I want to now predict the mileage.
More number of cylinders, that means the mileage would reduce, I think, because more fuel gets burned in a short
Yeah, yeah,
amount
yeah.
of time.
I think we should have a less number of cylinders because the more fuel goes in into that.
Hmm.
Yeah,
So
I agree with Aril's point.
okay, so if you have more cylinders, then the
Less mileage,
fuel
less mileage.
less mileage. Great. What about others? Sunil,
Dis uh,
Karthik.
Yeah, actually, there is some interference. Yeah,
Mm-hmm.
I can hear you.
So
Actually, there is some issue with my connection, so
I
I can
think
hear you now.
I think
okay,
vehicle weight is inversely proportional with MPG.
no. I'm talking about cylinders first.
Lakshmi, can you repeat your question once? Like I was disconnecting and connecting.
Okay, so here comes the questions. I'm trying to predict the miles per gallon for a vehicle, and to predict the miles per gallon or the mileage of a vehicle, what are the variables I am looking forward, and which are the variables from the domain point of view they are actually needed when I'm trying to predict miles for a car, okay, or the mileage of a car. Fine. What variables I should look into it. Somebody have told me that you should look cylinders, displacements, horsepower, weight of the vehicle, acceleration. So I want to know how cylinder is influencing towards mileage of any vehicle. So yes, when
I think there is no relation.
no relation is it? If you have, so I mean the mileage should not go up or down even when another cylinder number of cylinders are increase or decrease.
Yeah,
Just think. I mean, there is no harm in thinking. You just ensure
No,
that.
Lakshmi, I think it is like inversely proportional because I mean, in reality, if I see the bikes or cars which have the more number of cylinders, I mean, we can't say that is completely independent, but there will be some effect on the mileage based on the number of cylinders. The more number of cylinders, the more combustion happens inside the engine.
Hmm.
I mean, that is
So
what
more
my
fuel
understanding.
goes. Yeah, more fuel goes to engine,
Yeah,
and
correct.
your engine power goes increases. Okay, your
Yeah,
acceleration, you can accelerate with faster, but at the same time mileage also get impacted.
yeah, correct.
So it looks like from the domain angle, from technical angle, it looks like when I increase number of cylinders, the mileage should come down,
Correct.
isn't it? So here
Yeah,
I can see the collinearity between cylinder and number of cylinder and your miles per gallon or the mileage should be negative.
correct.
True? Yeah. So this is what I mean. We understood that there is a relationship exist, and what I see is the relationship is a negative relationship. Okay, when one increases, the other decreases. Okay, let's go to other variables. Displacement and engine displacement. Engine displacement with mileage.
It's again inversely proportional. The more the CC of the engine, the displacement, lesser the mileage.
So this is also inversely proportional, is it?
Yeah,
Yeah, that's
correct.
my understanding.
Yes, Lakshmi.
I mean, in the practical examples we see, the bikes or cars which have more CC will have the less mileage. I mean, that is one practical daily example we see.
Correct. So we see it is also inversely proportional, right?
Yeah,
What about engine horsepower?
Same,
same.
Lakshmi.
More horsepower, the less mileage.
Less mileage. Vehicle weightage?
Yeah, same.
I
Inversely
think we,
proportional.
I think vehicle weight is not relevant, Lakshmi. I mean, just my point of view.
No, it matters, but it depends
Not
on the
not
engine
as much.
horsepower. So I
Yeah,
think weight
yeah.
and horsepower are dependent.
I think
Acceleration?
it is inversely proportional. Acceleration is directly
Acceleration is
proportional.
again inversely proportional.
Okay. So
Yeah,
now
please, please.
somebody's music is ringing in my voice. Yeah, okay, good. Fine. Yeah, so we understood, right? I mean, we want to find out the prediction of a uh, mileage, but I need to find out which are the variables I should take. Okay, and also I should have some sort of knowledge how these variables are actually related to your response variable. Now, when I build the model, my assumptions, whatever I took it forward from a domain angle or I got from my domain expert, should be in line with what your model is telling to you. Okay, if your model is telling something else, what your domain expert have suggested, it means that there is something wrong. Either the something is within the model itself, or it could be the understanding of your domain expert, right? So so if there is a conflict arises between your domain expert suggestion and your model suggestion, then you have to go and actually do the investigation why the conflict have raised. Got it? So that's why you have to understand the domain, and then you have to also look at the response of your model. Okay, so that's what the context of this problem. Let's see what we see. Okay, so these are the variables. What I'm going to do is definitely my UI response variable is a continuous variable. Okay, and these are periodical variable. This is a periodical, this is a continuous, this is also continuous, and this is also continuous. Now all my x variables are continuous, y variable is continuous. Simply I can go back and try to build a regression model. Okay, so let's say in the regression model, the first step is I have told that we have to find out whether the variables are independent or not. Okay, what I can do, I can run a multi-collinear correlation matrix or covariance matrix. Now this is my chart of covariance matrix of the entire data set. Now see who are the variables having multi-collinearity problem. You can see miles per gallon have good relationship with the cylinder, displacement, horsepower, weight, and acceleration. Listen, this is what my model relationship. Now let's see whether the cylinder have a relationship with other variables. Now you can see cylinder have relationship with miles per gallon. Okay, cylinder have relationship with displacement with 0.94 and also have relationship with the horsepower with 0.75. It have also relationship with weight and acceleration, right? So these independent variables are somewhere related to each other. Okay, and this relationship is not good for your multiple, multivariate linear regression. I have to get rid of it. Hmm. Okay, so you can look into this slide. Okay, now you got it. So tell me how we represent a multivariate regression model. What this slide is saying is, now I say y is equal to, okay, what is the model? Beta 0 plus beta 1 x1 plus
Beta 2
beta
x2
2 x2
and so on.
beta 3 x3. Okay, so what is this beta 1, beta 2, beta 3?
The weights of the variables.
Yeah. So what it says is whenever there is a change of 1 unit happens in x1, then beta 1 units of change will happen in y. Okay.
Yeah.
You see the sign. It is a positive. This is also positive. This is also positive. Okay. From the domain point of view, it says whenever there is a change of 1 unit happens in x1, there will be a positive b1 units will change happen in my y. Okay. Now, if I build a model and I got something like that, y is equal to 26.
Lakshmi, can you change the color of that font to bit something more darker? Thank you.
Okay. Okay. 1 second. Let me erase it. So I build a model. I got something like that. Okay. Some values like this plus 2.1 x1 minus 0.6 x2 plus 1.2 x3. Okay, so here you see what I see the difference here. This is the model which I built. Okay, but in actual, this is what my a domain expert have told. The domain expert have told all these coefficients should be positive. What I see the difference here? Hmm.
Some are negative and some are positive. Yeah, the beta 2 is negative.
Beta 2 is negative. It says the beta 2 say which variable you want to take. You want to take the acceleration one?
Yeah,
Acceleration?
the, dis-
It
the
says,
displacement. Yeah,
huh, huh, yeah. So, or the displacement which is actual positive and your model says is negative. Okay.
correct.
Actually, the x2 is positive. X2 response to y is a positive. But here what I can see is I can see negative. It says that the model which I have built, it is actually is not a meaningful model. Something wrong in the model, right? Yeah, it could be because of multicollinearity problem, it could be because of something else. We have to go back and investigate your data. Okay, so there are certain steps you have to execute before you build your model, and PCA is one of them. Multicollinearity is one of the
Lakshmi,
biggest
one
problem. Huh.
that negative value, we got that negative value from the multicollinearity matrix, right?
Yes, so you have built the model,
Okay.
right? You have called LM function, and you found that it have given all the beta coefficients. It will give you beta 0, beta 1, beta 2, beta 3, like that. It will give you the coefficients. Now, one of the coefficient is beta 2, and there you found it is a negative, whereas your domain expert have told no, it should be positive.
Yeah, got it.
Okay, got it. So what you
Yeah.
should do though, you have to go back and again find out whether your data what you have taken is correct or not. Okay,
Mm-hmm.
let's see here what we have done. So I got the auto data. I have created my multicollinearity matrix. So you can see the variables like cylinder, accelerator, acceleration have a relationship with multiple other variables. Now what I need to do is how to get rid of it. Okay, so to get rid of it, I will try to plot which variable is causing the maximum problem, right? Or which variable have the highest multicollinearity among themselves. So that is what it is called, variance inflation factor. Okay, somebody have put this question, what is variance inflation factor? Variance inflation factor is nothing but the measure of multicollinearity. Okay, the VI provides an index that measures how much the variance of an estimation regression coefficient is increased because of the multicollinearity. Okay, so the VI should be close to 1. If it is greater than 5 or greater than 10, it's a horrible. Okay, you should not keep that variable, or you should try out other alternate options. Okay, so how I will get the VIF? Let's see here. See, the estimated acceleration is telling negative. Hmm. Others are negative. I think you guys have already told. So it is negatively related. It have given, but acceleration also it have given negative, where in reality it is positive. So I got that multiple r square and I got the adjusted r square. Okay. Now see what is the VIF for auto data. Now what I'm going to do is I will find out the VIF for all the variables. Okay. Variance inflation factor. Now I can see the horsepower have the highest VIF, isn't it? In the data set.
Yeah.
So what does it mean is if you see the data with the highest VIF or variation inflation factor, then drop that variable. Okay, so here what I have done is I have dropped the variable of horsepower, and then again I play the VIF, hence I found cylinder is the next highest variable which is having multi-cognitive problem with other variables.
Mm-hmm.
Okay, then again I found no, displacement is also a significant, it is 4.3. Let's drop displacement also. Now you have
Okay.
already dropped three variables,
Yeah.
right? So now you have taken only weight and acceleration, and weight and acceleration is giving VIF 1.
Mm-hmm.
Okay, so what I'll do is I will go ahead and build a model with removing all those variables who were creating problem for me. Okay, yeah. So it means that it is it is it is giving you a meaningful model, but it is not deployable in the target, or you cannot take this model to target, because most of the variables which are really important, because we are working on linear regression, so we have dropped it. Okay, what I need to do is I have to go back and see how I can how I can retain those variables. At the same time, I want to get rid of the problem. Here, the VIF is only the immature way of handling this problem, but it is not practically used in any industry. But the second approach for dealing with such problem is called principal component approach. Okay, so the alternate approach is called principal component, and then we will go and see how factor analysis also can be used. Okay, so let's understand what is principal component. So you guys have already, I believe, have gone through eigenvalues and eigenvectors, right?
Yeah,
So eigenvalue and eigenvectors is clear. Okay, great. So now yeah. So now what we are going to see is how the principal component is playing a critical role in removing your multicollinearity problem. So see, principal component is nothing but it's a uh, it's a derived variable which is based upon all your independent variables what we have. So what I'm going to do, I have 5 variables. Now what I'm going to do is I am going to derive 5 additional variables. Okay, and these additional variables, which are called principal components, they are completely orthogonal to each other. Okay, so I don't need to go back and see whether there is a multicollinearity problem is there in the principal components or not. I can directly take this derived principal components and build my regression model. Okay, so this is what I have done. Now each principal component is going to explain some part of your variation in the y variable. Like as we have seen that no, as I have explained, that adjusted r square is nothing but the amount of variation in your y variable is explained by all your independent variables, right? Now here what happens is, whatever the list of variables I have taken in my auto data set, they all are explaining the variation of my what response variable. Now what I'm trying to do is I'm going to take all those variables and trying to create some derived variables. They are nothing but principal components, and each principal component is going to explain some amount of variation in my response variable. Okay, now when I build 5 principal components here, the first principal component is going to explain the maximum variation in my response variable, and subsequently followed with other principal component. So principal component 1, the variation of principal component 1 is greater than the variation in principal component 2, and followed with 3, 4, 5. Okay, is it clear now? Clear, guys?
Lakshmi, can you repeat the last point over there? Variance of PC1.
Huh. So here, okay, very Sunil is he is sleeping, is it now? I will check with him.
let me check.
Okay, so here it is. Let's say, let me put it this way. I got, horsepower. Okay, what else? Acceleration. Yeah, then,
Displacement,
yeah, weight, displacement, and one more, cylinders, right?
cylinders. Yeah.
Okay, and this is miles per gallon. Okay, so this miles per gallon, uh, the values, let's say miles per gallon could be like 15. Okay, okay, it will be 17 something, 13, 12, and here some values, right? So, so this is the miles per gallon value, or the variable values are explained by all these variables. Hey, how much it will be, it is explained by all these variables, right? So now it is not possible that only these five variables are responsible for MPG. Yes or no?
Yeah, Lakshmi.
Yes or no? So now it may not be able to explain all the exactly what will be my miles per gallon. There could be 70% explainable or 80% explainable. Now what I am trying to find out is, whatever percentage is explainable MPG, these five variables, I cannot straight away use these five variables because they have a multicollinearity problem. Now what I have tried to find out, I have created five more derived variables. I have five variables, I have five derived variables. Okay, so they are called principal component, PC1, PC2, PC3, 4, and PC5. So each PC is a composition of all these five variables. Okay, and then it have created one variable. Okay, each PC is a composition of all these five variables. So it means that the variation in Y will be explained by PC1 as well, isn't it? Now what it's saying is, the amount of variation in Y is explained by PC1 is greater than PC2, and PC2 is greater than PC3, PC3 is greater than PC4. Okay, so the amount of variation in Y is explained in PC1 is greater than PC2, is greater than PC3 and 4. Now say the total explanation of all these variables is something like 80%. Okay, 80% is nothing but the adjuster R square, which is nothing but 80% time it actually correctly predicts. Okay, with 95% confidence interval. Okay, now this 80%, okay, also will be explained by all these pieces, but the first PC will explain the highest variation, followed with second, third, and fourth. Okay, now what I need to do I need to take all the pieces? What I can do is, I will take only, let's say, limited number of pieces which almost explaining the total variation. Now my 80% I can take up as 100% for this model. Okay, out of 100%, the PC1 explains, let's say 70%. Okay, followed by PC2 is explains 20%, PC3 explains 5%. So now if you see 70 plus 20 plus 5 is almost 95%. Now 95% of your variation in MPZ, okay, is explained, not MPZ, or the 95% of the total explanation. Total explanation, I can say 80%. Out of 80%, the 95% is already explained by PC1, PC2, and PC3. What I will do, I can drop out PC4 and PC5. I can just take PC1, PC2, PC3, aggregate them, and tell them, okay, this is what my model is, and this model independent variables are completely orthogonal, and they don't they satisfy all the assumptions, and this is what my accuracy of the model. So if you give the proposition like that, then it will be making sense and it will be acceptable. Okay, so that's what the concept of PCA. Now what we can do is we can go back and study how PCA is going to be designed. Okay. Okay, so how I create the PC ones, the principal components, as I told, each principal component is a composition of all the variables. Now in my case I have 5 variables, and each PC1 is something like a1 x1, a2 x2, a3 x3, a5 x5 with am x xm if I have m variables. Similarly for PC2, PC3, PC5. Now PC1, PC2, PC3, PC5, they are all orthogonal. They are nothing but eigenvectors, and each eigenvector is a orthogonal to another eigenvector. Okay, now the variation of PC1 is nothing but, I can say, lambda 1. Now lambda 1 is greater than lambda 2 is greater than lambda 3, lambda m. Okay, so is it clear till now?
Yeah.
Yes, like
Okay, so understood what is a principal component, why principal component is created.
Yeah.
yes, like
Yeah.
Okay, so now, yeah, so I have taken the variance also. You can see the variance, the I mean, you can have multi-collinearity matrix or variance matrix. It says, okay, you can remove it. How I can get the principal components? Okay, I want to get the principal component, individual principal components. I can get by just calling PR comp. Okay, PR comp, you take the auto data. Okay, and then you can get the all PC1, PC2, PC3. And okay, so you can see this APC1. This is nothing but you will be getting the principal components. Summary will go back. Okay, right. Now let's see here. So PC1, PC2, PC3, 4, and 5, it is giving, and proportion of variance is it have given the standard deviation and proportion of variance. So you can see the PC1 is explaining 77%. Okay, PC2 is explaining 17. Okay, PC3 is 0.04, PC4 is 0.01, and cumulative it is saying, if I take PC1, PC2, 95, 90, almost 94% of variation is explained. If I take PC3, almost 98% of variation is explained by PC1, PC2, PC3. I don't need PC4 and PC5 to build model. Okay, now you can see the variance. Okay, what is the variance? So each, now PC1, PC2, PC3, PC4, all together, how much variance they are explaining? Nothing but you add up their standard deviations. Okay, if you add up this standard deviation, it will be coming as 3. Okay, I think 5. How much is coming? 2 or 3, 3.5, Okay, total is 3.8. Is it total 3.86? Can somebody add it? Mm-hmm.
Yeah, Lakshmi, I think it's around 3.6.
3.6. Okay, so what it is telling is what is the percentage of variation in my response variable is contributed by individual principal components. I can see the first principal component is already explaining 0.77, followed with 0.17 by the second principal component, and followed with third. Okay, so here you can see this is the variation, and how the you know how the variation is explained, and it is completed. So total variance is your 4. If you add up all the standard deviation, it will come up to 3.86. Now the first and second itself is almost explaining your 70% or 80, 94%. 94% of variation is explained by only two principal components. Okay, and if you take third one, I think third one is 98. So 98% of variation is already explained by 1, 2, 3. So you don't need to stretch out and try to get those values also. It can be removed. Okay, it can be dropped out. This is what it's saying. First two pieces explain 94% of total variation. So we can, if we are okay that 94% variation in my y response variable is good enough, then I will not go to the other principal components. I can straight away take principal component 1 and 2 and build my model. Yeah, please go ahead.
No, no, Lakshmi, nothing.
Okay, fine. So is there any questions? Clear?
Lakshmi, sir.
Yeah. So I have built the principal components. Once the principal, okay, you can see this. It says each principal component, I think eigenvalue, eigenvector. If you have understood, this is not nothing but my eigenvector. The PC1 is a eigenvector. Okay, PC1, PC2, PC3, and all these eigenvectors are orthogonal to each other. Okay, there is no relationship among them, and each eigenvector I represented as a no, composition of all your independent variables. Okay, so this is what it is says. Okay, so PC1 is giving me is 48. No, yeah, this one I can see, right? So I found the PC1 is 0.48 multiplied with cylinder as a minus 0.48 multiplied with cylinder plus minus 0.48 multiplied with the displacement plus minus 0.48 multiplied with horsepower plus minus 0.43 multiplied with weight plus 0.34 multiplied with acceleration. So all this together build the PC1. Okay, you can see here. Similarly, all this together build PC2. Now one PC1, PC2 enough. So how I am going to build this regression model? Let's see. Here what I have done is I have 100 records, right? Let's say, let me show you that record. Okay, see, cylinder displacement, horsepower, weight, and acceleration. Now I'm going to do a PC1, PC2, PC3. Okay. Okay. So 1, 2, 3, 4, 5. So what is PC1? We have seen already.
So minus
A1, X1.
0.48.
Yeah. So I
Yeah.
already got the A1, A2, A3, isn't it? Where is it? A1, A2, A3. I can multiply those X1, X2. So these are my X1, X2, X3, X4, X5. Here I already got my values. Okay, isn't it? So I need to multiply it minus 0.48. So here what I need to do is, okay, minus 0.48 multiplied with
Into 8.
what?
Into 8.
Ah, into 8. Hmm.
The next 0.48 into 8 again. No, 360.
Hmm. Minus
0.48 into 360.
hmm.
The next, what is that value, Lakshmi? The A13. Just can you go
Which
back
one?
to your slide? The A13. Can you just go back to the slide? Yeah, okay, all 0.48. Okay, got it. Yeah, yeah. Then now 0.48 into horsepower. So that is 175.
So can I get this value like this? I can get
Yes, you
it, right?
can, Lakshmi. Yeah.
So I can get PC1, PC2, PC3, PC4, PC5. Okay. So I
Correct.
can fill this field with the PC1, PC2, PC3, PC4, PC5 values.
Yeah.
And this is my Y response variable, right? Now, what I'm going to do is instead of taking all these variables, I'm going to take these variables. Okay. I'm going to take these variables. Okay. I can reject these variables. Hmm. This you can leave it. So populate this PC1, PC2, PC3, PC4, PC5 out of your MPG cylinder displacement, horsepower, and acceleration, and you maintain this Y response variable, and then you take these variables and build a linear regression model. Okay, clear or not?
Yeah,
Yeah,
got it.
Lakshmi, clear.
Yeah. So once we have done that, let's get the PC score. So I have got the PC score, which I have explained in the Excel sheet, the same thing, and then you can do the plotting. Okay, what kind of plotting I need to do here? What kind of plotting?
Line plot.
It is a scatter plotting.
Scatter
Yeah,
plot.
it is a scatter plot, isn't it? And we have given some colorings also. Okay, so it is just a regression. I have plotted this y response variable. Okay, and then I can see whether is there any linear regression exist or not. If there is a linear regression, you can see here clearly it is growing. Okay, but there are a lot of variations, right? Now already, so if you take the PCS and then try to get their no multicollinearity by using uh, whichever methods I have suggested. I mean, multicollinear matrix or your covariance matrix. What you will find is it is a completely orthogonal and it is not having any kind of no, uh, relationship among themselves. It is always zero, right? So now once orthogonal is completed, what you can do is you can build your regression model. You take all the PC1s, PC2, PC3, PC4, PC5 if you want, or you can take only PC1, PC2 if you're happy with the 94% you know, um, Y response coverage. And if you want to have some other additional project specific information, that also you can add it up. Okay. So what is project specific? Project specific means the model says two variables is enough. Okay. But in my project, what I have is I have hundreds of variables. I have built a PCA of 100 variables. Now, if I take 5 variables, it is giving 78%. Okay. And if I want to make more complicated and with more new additional variables, I can go ahead and add it. But the problem is it should be limit to your project. I mean, it should be acceptable from your, delivery head, or it will be data scientist, something like that. Okay. Then I have done the regression using PCA. I did the regression and I can see the estimators. I can see standard error, t values and p values. This is as usual. So what is the conclusion? Conclusion says regression with PC improves the regression fit. Predictors are uncorrelated. VIF is 1. Regression is more stable. Prediction is more user friendly. Okay. So in with this, I can say PCA is complete, and what I can do is I can take up a sample code and run and show you how it is working. Okay, so I've installed library car. So you guys have to install car library. Read the CSV file. So this is what my correlation matrix. This is my code. Okay. Then what I did is I built the model, which linear regression model with as it is data without making any changes. And then I have tried to plot that, not changing data set. And we can see these variables are related, but they are not related with a proper sign, especially acceleration. Okay, so what I will do, I'll make the VIF, right? So I have, this is my multi-community multivariate explanation model, and I can see the response with F. Yeah. Okay, so okay, okay, so I got the A fit to, I can give the summary and draw my conclusion, right? So it says the acceleration is positively related, okay, which is not true. Now I can summarize this. Then I run again linear regression model by removing one variable that is that was troubling during all right, you know, our VIF. So I have removed the VIF. I kept only two. I have remove here. Then I have removed one more. Okay. So now I got a cylinder which is 10.47, displacement 9.76, weight and acceleration. And then I build the model. Again, the fourth time I remove another variable. Okay. Yeah. Now I am creating the principal components. Okay, you can see pre-comp is creating my principal component. Okay, and then I can plot the my principal component in a graph and see where the elbow is moving, or it is becoming flat. This is my elbow, right? This elbow is kind okay, but 83% is definitely not okay. Maybe you need more. I got it. Okay, this is all only I got the principal component one. Okay, I plot it, then summarize the principal components, and then I also got, yeah, sequence points plot. This is, I plotted all these things, and I combined auto 1, PC1, PC2, and auto. Here it is giving the my principal components, and from principal component I am getting what I am doing is I'm getting only the PC1 and PC2. You see here, I'm not interested for 3, 4, 5 because I don't want 3, 4, 5 because they are not making much sense, because with two principal components I am getting almost 92%, and I am happy with the 92%. I don't need more. Okay. Yeah. And I have taken this um, principal components. I have taken two principal component, and I have taken the y response variable and build the linear regression model. And whichever is working or meaningful, that I have taken.
Lakshmi, actually, light was off. So I did not have any internet. So now I see.
Oh, okay. So entire we have completed principal component.
Okay, this is
Yeah, no problem. I have recorded.
okay. Okay.
There is a or okay, guys. So is there any question on here?
No questions, Lakshmi, from me.
Okay. So um, that's how the principal components are evaluated. What you guys have to do is I'll give you another set of data. Yeah. And you have to derive those principal components and uh, now use them for your prediction. Okay, first you have to see whether there is any sort of multicollinearity problem is there. If multicollinearity problem is there, then find out which are the variables are creating problem, try to get the VIFs. Okay, and then try to apply the principal component and build the principal component and use those principal component to build your model. Okay, and sort out how many principal components you really need to build your regression model. Okay,
Yeah.
so the R script is there, but definitely you don't follow the R script as it is. You have to go and do little study. Okay, and then you refer to the R code.
Lakshmi, one question. Ideally, there will be the number of principal components will be equal to the number of variables we have, right? Ideally.
Yeah, this is what number of principal components equal to number of variables. That is how the principal components will be created, but you don't need all of them because
Yeah, that's
the
what we
yeah,
take into the model is a different one.
yes, you will
Okay,
be
got it.
finding. Yeah, this is what.
The percentage, how much weightage each principal component will have, and we'll based on the accuracy 94 or 98, we will take those many principal components.
Yes, yes, that's all. Okay,
Yeah,
so
Lakshmi.
that so even that's what. So what I can do is I will give you one assignment. Yeah, you can work on it. Even you today only you can work on it, and tomorrow we will discuss about the factor analysis. Okay, when factor
Okay.
analysis also. What I can do is I can give you a little bit background about the factor analysis so that no, you guys also have a little bit of brush up. Let me tell you what is factor analysis. Now see, I have created these principal components, right? Okay, I created five principal component, two principal component. Now, if I want to take this model and go to the business team, okay, what you will explain to business team? You will tell, okay, see, I have created this principal component, and these principal components, if are actual the factors which is going to help you out to predict what will be the demand for next year, or what will be my mileage for the vehicle, all this blah blah blah. But is business management team able to interpret these principal components and tune their business? No, right? You cannot relate principal components to any real time, or I mean, what I can say, real time, any an incident or any variable which you can tune it, isn't it? Here, like horsepower. Okay, horsepower. I have to. Okay, I want to build one vehicle. I have to tune the horsepower so that I will have a better mileage. Okay, or I can reduce my cylinders, or I need to reduce my weightage in order to increase the fuel efficiency of my vehicle. But if I tell you, okay, I got principal component 1 and principal component 2, if you increase the principal component 1, you can increase your fuel efficiency. Now, how you can interpret these principal components with real time, something relevant variable or something relevant item? Okay, so that is where the PCA is not going to work. What we need to do is we have to come back and study something called factor analysis. These factors are actually derived variables which is having a industry relevance, and which is built upon PCA. Okay, you got the PCS, but on top of that you will be creating some industry or domain relevant derived variables which actually you can interpret them. Okay, and they will be based on the principal components of analysis. Okay, this is how the factor analysis comes to picture. Okay, I'll give you one example. Let's say you want to bring up a new television to the market. Okay, now when you brought up new television, what are the how you will try to reach out to customers? Now you have to understand the customers about their preferences, right? Now customers will be looking forward TV quality. So TV quality, when you say picture quality, audio quality, right? Your display quality, all these qualities will be people always looking forward a better value, isn't it? Yes or no?
Yeah, Lakshmi.
Like that. There could be other factors like let's say the services. So you will be finding whether delivery is good or not, whether the if there is any effect happen, or the maintenance services, or the delivery services, or technician services. These are all attributes you will be putting and trying to see how the customers are rating any product based on these attributes. Okay, now you put hundreds of attributes. Okay, let's say you put five quality attributes. If somebody is looking forward for quality, then definitely he will tick all these 5 attributes. Yes or no? He will put,
Yeah,
okay,
Lakshmi.
I want a picture quality. I also need to see the video quality. I also need to see the display quality. Okay, based on that, I decide whether I will go for a particular television brand or not. Right.
Correct.
So what it says is, now you can tune the picture quality, you can tune the video quality, but all of them together, they actually represent one derived variable that is called nothing but quality. Right. Similarly, in services also, you will be having 10 or 15 services, all are which no, which is related to some of your activities in the industry, but they all together related and they are represented by a derived variable that is called services. So in factor analysis, what we will be trying to find out is one thing is principal component have one issue, that it doesn't have any industrial relevant. Okay, another thing is, if you have hundreds or mm, no more than hundreds of variables, which is very difficult to measure and monitor them, what we do is we try to combine these variables based on their similar characteristics. Okay, now I see all the services can be combined together and I can have a one single service attribute. Similarly, all type quality attributes I can combine and I can come back with another attribute called quality. Now see, 5 quality attributes combined and brought up one quality attribute, 5 services combined and I brought up one service attribute. Similarly, when you have hundreds of variables, you will try to find out who are the variables are similar characteristics, combine them together and represent by their one factor. Okay, again, and all these factors also should be what, independent to each other. There should not be there should not existence of multicollinearity, right? So here also the PCA also come to picture. You should have uh, PCA, and on top of PCA there should be a factor, and these factors are actually used for your business problem solving. Okay, so this is what I mean. You got multiple you got linear regression, you understood multiple linear regression, then we went to uh, principal component analysis, and then we are going to understand factor analysis. Once factor analysis is done, then we will take up a completely real-time use case and we will try to solve them, and there we are going to understand what the significance of multiple r square, significance of adjusted r square, how to sort how to decide which variable I should take, which are the important variables actually contributing towards explaining maximum variation in your response variable. So all these things we have to look and understand when we look for a case study to solve. Okay, so now you guys go back and finish that the assignments which I have given. Look again, go through the principal component no I mean whatever materials I have sent, and again run through the R script and dataset what I have given. Yeah, and then come back with fresh mind tomorrow. What we are going to do is we are going to talk factor analysis in detail, and and then we will talk about a case study for the regression, and then we will close the regression analysis. Okay,
Yeah, Lakshmi, sure.
Yeah, okay.
right. So
Krishna, do
Sunil,
you have another data set?
I'll give you
What,
another
Lakshmi?
data set. No, Sunil, so you have missed some of the classes.
Yeah,
Are
Lakshmi.
you, yeah, are you comfortable with regression?
Regression, I'm reading of my own, Lakshmi, with your materials and all. So, um,
till this far regression is okay, but
Hmm.
some doubts I'm facing. I will try to figure it out, and I'll ask you. That day also I said,
Yeah,
right,
yeah.
I had something to talk. For that only I was telling.
Yeah, yeah. Sunil, you can call me anytime, okay? But you don't miss the classes or you don't get not distracted, okay?
Yeah,
So
Lakshman. That's noted.
because you see, I feel you are the most no probable guy who can get into data science immediately because you are already there.
Yeah, Lakshmi, but this brother's engagement was there, and this all thing,
Hmm.
so I could not help myself.
Yeah, yeah. But you spend time, and otherwise, no.
I'm looking into it on I'm reading it, Lakshmi, and I have doubts. I will ask you. What,
Sure, sure, sure. I mean, definitely. Hmm.
probably next week when you conduct a means offline class, there I will ask you.
Sure. Yeah, not today we are supposed to do no classroom training, but yeah, unfortunately we could not do that. Auto data. Let me see that. Okay, this is what we have covered, right? Hmm. This is done. Anyway, we have discussed already this. Hmm. Yeah, heteroscedasticity, I will talk once we complete the factor analysis. These are something actually part of your response variable. Hmm. Only heteroscedasticity will be remaining. Otherwise, I think I have done with all. Let me see PCM metals. So what I want. Hmm. Okay. Anyway, this anyway we'll talk about. Yeah, fine then. I will give you another PCI assignment for the no study. But you guys go back and study it. And factor is one more no important no concept which we need to understand. Yeah, and please complete that linear regression assignment. If you guys can complete it today, we can have a discussion tomorrow.
Okay, Lakshmi.
Yeah, and tomorrow there will be classroom training, 10 to 12. Be there in Avoma.
Yeah, sure, Lakshmi.
Okay. Yeah. 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 That's all, guys.
Thank you.
Thanks, Lakshmi.
Lakshmi,
Yes. Yeah.
can you see that one?
Which one?
I had
So
uploaded
you
in my
sent the assignment. Yes. Yes.
yeah.
I will go through your assignment. Okay. Yeah. I'll come back. Hmm? Or you want
Yeah.
me to look it now? Let me go through it. You have already
No, no.
sent.
Whenever you want, it's not now only.
Definitely. We will. No. What I want is all of you just complete that at least the linear regression assignment what we have given. So all together we can solve tomorrow's class.
I think some error is there because I was speaking about adjusted R square. There, I can see only 30% is there. So it was
Oh.
supposed to be 80%. So I think some error is there. That's why I wanted you to review it so
Okay.
that I can change it if. it is needed.
Yeah, good that you got 30% at least. You passed then.
Yeah.
Okay. Yeah, anyway, we'll take that assignment in the classroom tomorrow. Hmm.
Okay.
So let's complete this assignment. Okay. Yeah.
Okay.